This video is part of the MCAT Chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to cover galvanic and electrolytic cells, and we'll specifically look at spontaneity, concentration cells, and the equations that you need to know. Electrolytic cells use the same principles that we talked about in the last video, where we have a metal that has a higher reducing potential than another metal, and then the ions are able to take the electrons from the metal with that lower reducing potential. And if you need to learn more about that, then go watch the previous video because that covers it more in depth. So keep those principles in mind, and then we're going to break down these images or these diagrams that we have right here. On the left side, we have a solution with aluminum ions, and then we have a strip of metal right here that is solid aluminum. And then on the right side, we have a solution with lead ions, and then a strip of metal that is solid lead. And then connecting those two metal strips, we have a wire, which is that gray line right there. So this is kind of like the situation in the previous video where we had a metal strip that we were dipping into a solution that had metal ions in it. But this time we just have these two solutions that are separated but connected by this metal wire. And what you want to think of now is, based on the reducing potentials of the lead ions and the aluminum ions, which one is going to be able to steal electrons from the solid metal strip that's in the opposite container. So for example, can the aluminum ions over here take electrons from the metal strip of lead in the other container? Or can the lead ions take electrons from the solid strip of aluminum in the other container? And the way you figure this out is just like the other video where you compare the reduction potentials. Remember that these values tell us how likely will the ion gain electrons, or how strongly will the species on the right side hold on to the electrons. So let's first think about, could aluminum take electrons from lead? So aluminum ions have a value of negative 1.66 reducing potential, and they are going to try to steal electrons from solid lead. And solid lead holds on to electrons with a value of negative 0.13. So negative 0.13 is greater than negative 1.66. So that means that the aluminum ions do not have the strength to steal electrons from solid lead. Now let's think about the opposite. Can the lead ions take electrons from the solid aluminum? And using the same logic, we can see that lead ions are trying to gain electrons with a power of negative 0.13. So because negative 0.13 is higher than negative 1.66, the lead ions will be able to take electrons from that solid aluminum strip in the other container. And those electrons are going to travel through this wire all the way to the other container. So in the container on the right, we have the reaction that is lead 2 plus gaining electrons to turn into solid lead, which means, like we said in the previous video, you're going to have a buildup of solid lead in this container on the right. And the amount of lead ions, the concentration, will be going down. And on the left side, the aluminum solid will be turning into aluminum 3 plus and losing electrons, which means the concentration of aluminum 3 plus on the left side will be going up. Eventually, hopefully you can see that the aluminum strip on the left side is actually going to gradually be dissolving, and eventually it's going to completely dissolve and we're not going to have any aluminum on the left side left. And then again on the right side, eventually we're going to lose all of our lead ions. So eventually this reaction is going to stop once all of our reactants are used up. The last thing you want to look at for this setup is this K plus Cl thing that we have connecting the two containers. And this is our salt bridge. Remember what we said about over time, the aluminum ions are going to be increasing in concentration on the left side because that metal strip is turning into ions as it loses electrons. So we're going to have an accumulation of positive charges. So over time, all of these aluminum ions are accumulating and creating a really positive charge in this container, which, if we want electrons to be leaving this container, that's going to make it really hard for them to leave. So the salt bridge allows for chlorine ions to dissolve into solution to help negate some of that positive charge that's building up. And then on the right side, we're losing those lead ions because they are combining with electrons and forming solid lead. So to offset that loss of positive charge, we have potassium ions that are dissolving into that solution. So the salt bridge is there to just kind of help offset some of the changes in charge that happen during the reaction. The last thing you want to be able to do is calculate the reduction potential of the entire cell, which we talked about in the previous video as well, and it's this equation down here. And it's simply the reduction potential of the cathode minus the reduction potential of the anode. Something that cannot be stressed enough is that no matter what, the electrode that gets reduced or the metal that gets reduced is always the cathode, no matter what. There will never be any exception to that rule. So in this situation, find your cathode, and that is the one that's gaining electrons, so it's the lead. So we need to find our reduction potential for lead, which is already given to us, it's negative 0.13. And then we subtract the reduction potential of the anode, which is always the electrode that gets oxidized. So aluminum is getting oxidized, so we use the reduction potential of aluminum in this equation, which is negative 1.66, which gives you a value of 1.53. Now make sure that you never change the sign of the reduction potential for the anode. People do this a lot because they know the reaction is actually solid aluminum turning into aluminum 3+, so they want to change the sign of this. But notice how in the equation it is asking for the reduction potential of the anode. So the way that this reaction is written right here is showing a reduction reaction, which makes this value negative 1.66 the reduction potential. If you flip the value and you change it to positive 1.66, then that is the oxidation potential. And that is not what this equation is calling for. When you're taking the test, be on the lookout, and if they're ever giving you values like what we have on the right side here, they should tell you if it's reduction or oxidation with a little subscript right there. But if they don't, pay attention to the reaction that they correspond to. If the gaining of electrons is on the left side of the reactions, like what we have here, then that means that the values on the right are reduction potentials. If the gaining of electrons is on the right side, like what we have right there, then the value that they give you on the right side means that it's the oxidation potential. Once you plug the appropriate numbers into this equation, the value of E cell tells you whether or not it's a galvanic or electrolytic cell. If it's a positive value, then that means it is a galvanic cell. And galvanic cells are always spontaneous, which means if we set this reaction up, it's going to happen on its own. Which brings us to the next point, which is electrolytic cells, and we're going to use the diagram on the right side to show what an electrolytic cell is. Notice how on the right side we have the exact same setup as the left side. The only difference is we're going to take this galvanic cell and we're going to plug it into an external power source, and we are going to force the electrons to go the opposite direction. So naturally the electrons want to go to lead, but we're going to use this external power source to force them to go to aluminum. And the biggest thing that you want to realize now is that aluminum is the one that is getting reduced, which makes it the cathode. Because remember, there are no exceptions to that rule. The electrode that gets reduced is always the cathode. And that makes lead the anode. From here, everything else is applied the exact same. So if you're calculating the E cell of this, you use the exact same equation. The only thing that has changed is you have a different cathode and anode. Now your E cell becomes negative 1.66 minus negative 0.13, which gives you negative 1.53. So notice your E cell is now negative, and that means that we have an electrolytic cell, and it also means that it is non-spontaneous, which that means that this direction of the flow of electrons cannot happen without the input of external power. So if we create this setup and we don't have external power, then the electrons are going to flow the other way. And a real world application of this is simply batteries. Think of the galvanic cell on the left as the usage of a battery. So maybe you've put a battery in a remote or something. Over time, that battery gets used up, and then the electrolytic cell would be recharging the battery basically. And we're forcing the electrons back to their original source so that we can reuse the battery again. The last thing you want to do is memorize which electrode is positive and which electrode is negative in these two situations. And I would not worry about why, which is which, just memorize this. So for a galvanic cell, your cathode is positive and your anode is negative. And then for an electrolytic cell, it's the opposite. Your anode is positive and your cathode is negative. Understanding the setup of galvanic and electrolytic cells is by far the most important thing about electrochemistry, but there are a couple equations that you probably do want to have memorized. The first one is just finding delta G whenever you're given the reduction potential of the cell. and it's going to use this F, which is a constant that they should give you on the test. E is the reduction potential of the cell, which we just talked about extensively, and then N is the moles of electrons that are being transferred during the reaction. And you get N through the balanced redox reaction. And we mentioned this in the previous video that eventually the number of electrons will be useful, and here's when this occurs. Pause the video, balance this redox reaction, and then I'm going to put it on the screen, and then we can see what value we should be using for N here. Here's the balanced redox reaction, and just remember to cross out what appears on the left and the right side. So we have 6 electrons on the left and 6 electrons on the right. So those do get crossed out whenever you write the full reaction, but that is the number we're going to plug in for N, because there were 6 moles of electrons transferred for this balanced reaction. So you'll just plug that value in with the rest of your values, and then you can get the delta G for this reaction. Whether or not E is negative or positive will also determine if delta G is negative or positive. And remember that a positive E was a spontaneous reaction, because that will make a negative delta G if we plug that into this equation. And then a negative reduction potential would mean it's a non-spontaneous reaction, and that also makes sense because if you plug that into this reaction, you will get a positive delta G, which means non-spontaneous as well. Lastly, we have the Nernst equation, and for this one, what this tells us is how we get from E naught, that symbol there is called naught, to E without the naught. So E naught means that we're at standard conditions. So everything we've talked about so far has assumed that we're at standard conditions, which usually that is going to be what the test is going to give you. But this equation allows us to take that value, and then if the concentrations of our substances are changed, we can still find the reduction potential, but just not at standard conditions. Remember, at standard conditions, we assume that the concentrations of our reactants and products are equal to 1. That is the purpose of Q in this equation. Because remember from equilibrium, and go back and watch that video if you need a refresher, Q is equal to the concentration of the products over the concentration of the reactants, and then raised to their coefficients. But it's simply at whenever we measure it. So this is not at equilibrium. The concentrations are not equal to 1. It's just whenever we decide to measure this, that is what gives us Q. So if we plug in the value for Q into that equation, it's going to give us the actual reduction potential at those current concentrations of the products and reactants. The last thing we have are concentration cells, and these are really unique because the same material is used for the anode and the cathode. So if you remember that equation, E cell equals the reduction potential of the cathode minus the reduction potential of the anode, we would end up with a value of 0 for concentration cells because it's the same value for the cathode and the anode because it's the same chemical. But remember, because of this sign, this not sign, that means those are the values at the standard conditions. And for a concentration cell, we are not at standard conditions. In fact, that is the definition of a concentration cell, is that we have these different concentrations of this same chemical. So for our example, we have copper, and on the left side, our solution has a 1 mole concentration of copper, and the right side has a concentration of 10 molar. So the right side is way more positive, so it is going to be pulling electrons to the right side. So in a concentration cell, the electrons always flow towards the electrode that is in the solution that has a higher concentration of that positive ion. And as long as they're flowing to the solution that has that higher concentration, we will have a positive E cell, and it will be spontaneous. And that means that it would be a galvanic cell. And to calculate the reduction potential of a concentration cell, we use the equation that we talked about previously in the video that uses Q, because Q is going to allow us to adjust for those different concentrations of copper in those two solutions. Out of all of this, what's most important is from the beginning of the video that you understand the setup of a galvanic cell. And then you're able to think through how you can take a galvanic cell and make it an electrolytic cell by forcing the electrons to go to the opposite side. And then you want to be absolutely crystal clear on what makes something a cathode and what makes something an anode, and then be able to calculate the E cell for that entire reaction.